The whole thing.
All right. Basically the same announcements as yesterday. We have exam review tomorrow. We have exam on Friday. I have written it, so I can answer some basic questions about it. Let's see, what else? We have an assignment due next week that I recommended people get started on. Does anybody have any other questions about the study guide? Anything else about the exam, things related to the exam? Good.
There could be questions, something like programming, thing like that. I can't remember the one.
Yeah. Yeah, there is a programming question. So there will be something very similar to that style of question where I have you solve some kind of problem.
Too much to ask what the subject is with that.
One of the things on the study guide. There are a few things I can do with each of those topics, with the exception of stacks, because I said there would not be any implementation on stacks. So it won't have to do with any stack implementation. Other questions?
Like the written examples, like when you write the code, is that gonna be like, is that what we ask more on stacks or?
It would be less on stacks for code, because I said there wouldn't be any implementation related to them, so it is some other time. Anything else before we get started with one of the more exciting topics of the course, in my opinion? I know we're probably pretty sick of sorting already, but now we get to start sorting efficiently, which is very exciting. All right, we'll get to it. All right, so I remember the mood I was in when I wrote this thing. The sorts we have covered so far are intuitive. Yay! The sorts we've covered so far are slow. Boo. So that is basically the entire motivation of introducing advanced sorts is we want to, this is always a trade-off in computer science, or very frequently a trade-off. Intuitive means slower. Faster means a little bit less intuitive. But you also get to start seeing the fun that we can have as we do something along these lines. So before we had covered recursion, and that was unfortunate. We could talk about the basic sorts that didn't require recursion, but now we're starting to get into some sorts that we've unlocked a much easier way of doing them now that we can think recursively. So before I've talked about how there's a perfect, whenever you have an iterative solution, you can make a recursive solution. Whenever you have a recursive solution, you can make an iterative solution. So nothing about the sorts that we're going to go over require recursion. It's just highly recommended, because if you don't do this recursively, it's kind of gross. So we're going to introduce merge sort, my personal favorite sort. And in fact, have you done something like arrays.sort or anything built into Java? They just used a dot sort. Java's built-in sort is merge sort. So if you've ever called dot sort, you've actually, underneath the hood, done this logic. But it is useful to understand exactly how it is done so that you know. So we are going to assume we have an array of random integers, just assume that they are not already sorted. If we were thinking recursively, and we wanted to sort an array of integers recursively, how would we do something like this? What would a base case be?
Size is equal, less than or equal to 1.
Yeah, an array of size 1 is already sorted, right? So base case, array of size 1 is already sorted. Let's break this down into some large scale steps, because if we do this, then we can work on solving each of these steps individually, and it'll be a lot less overwhelming than thinking about the entire process from the bird's eye. So let's start with the bird's eye, and then we'll break it down and solve each of these individual parts. So first, instead of lopping off the first element or the last element like we did to reverse a list, we're going to split the array in half. We're going to recursively call this procedure on the left half and the right half. And voila, we've made two arrays that are half the size of the original. And you can imagine as you split the left half in half, then you have arrays that are a quarter of the size. When you split those arrays in half, you have arrays that are an eighth of the size. And eventually you break it down into arrays of size 1, which are already sorted. So rather than thinking about that entire process, we split the array in half, we recursively call merge sort. Some magic is going to happen that we will later have to define. But eventually, up the recursive chain is going to come two halves of the array that are sorted. Somehow. So we're just going to wait for the recursion to do its thing, come back, and we'll get a sorted left half and a sorted right half. Now, there's no guarantee that the sorted left half is the first half of the array. And there's no guarantee that the sorted right half contains the latter half of the array. Since the smallest element doesn't necessarily have to come in the first half of the array. It could have come in the second half of the array. So we end up with two sorted arrays that we need to merge together into a single sorted array, thus the name merge sort. So we want to merge these two sorted lists into a single sorted list and return that single sorted list. So the way we're going to do this is we need 3 pointers. We need one at index 0 of each sorted array and one at index 0 of the empty but being filled array. Then we want to loop the following, because we want to fill this fully sorted array. We need to compare the values of what's pointed at the two indices. Do we agree that the smallest element in the entire sorted array either needs to be at index 0 of the left half or index 0 of the right half? Does that make sense? Why the smallest element has to be in one of those two places? We return two sorted lists. So the smallest element of the left half is at index 0 of the left half. The smallest element of the right half is at index 0 of the right half. So what goes at index 0 of the fully sorted list is one of those two elements. We just need to figure out which one. Whichever one it is, we're going to copy that over into the new sorted larger list at index 0. We then need to bump up the counting pointers in both the sorted list and the array that had its index 0 copied over, because we already considered that element. So now we're going to consider index 0 of the list that we did not copy over and index 1 of what we did copy over. And that is the loop. We loop back around and now say which of those elements is smaller. We bump that up. Which one of those is smaller? We bump that up. Which one of those is smaller? We bump that up. And we're just going to copy over every element until we have a filled full array. That's merge sort. That's the magic that makes it all happen down the recursive chain, is that entire merging procedure. So when we say wait for the recursive calls to come back with a sorted left and right half, this merge procedure at deeper recursive levels is what produces that. So we're going to go through examples of this procedure on the board so that hopefully it starts to make a bit more intuitive sense. And then we're going to implement it Because what good is theory without seeing how it works? Which of these pens has the most juice? Enough for today. Any questions about this procedure before we go get an example of it? Yeah,
I think you're gonna answer it, but what is if the people,
if they're equal, then it doesn't matter. You pick an arbitrary, break the tie inside. Other questions? All right, we're gonna do an example on the board. So I'm gonna make an array of size 8 because it's a nice power of 2. What I need from people are random numbers.
17. Yeah. 24. 8. 1.
All right. This is good. I think this will identify merge sort very nicely. So the first part of merge sort is breaking it down into its left and right components. So we need to figure out, one, where is the middle? The middle is right here. So we're going to split this into a left half and a right half, where the left half is the first 4 components and the right half is the last 4 components. So we're gonna have 17, 3, 34, and 10 over here. We're gonna have 9, 120, 8, and 1 over here.
How about if it wasn't even, if it was like 9 instead of 8?
If this was 9,
Like,
If there was a little bit.
oh, if this was 9, then one of these would be size 4, one of these would be size 5. The question of how you break that tie is irrelevant as long as you stay consistent. So yeah, I'm doing a nice power of 2 for illustrative purposes, but it will still work with arrays of other sizes as long as however you break that tie and where is the middle. Usually that's done via integer division, so you'll say that the middle is slightly, yeah, it's slightly more to the left, which means that this would be size 4, this would be size 5. It's a great question though. So if we're doing this recursively, usually you call this on the left half before you call it on the right half. So we need to solve the entire left subproblem before we even think about solving the right subproblem. So basically we say, how do we sort this? And we split it into a left and a right, and we wait for it to be sorted. The left and right has to be sorted before we can do anything here. Moving down here, this is gonna be the left, we need to break this into the left and the right, and we need to solve that before we go try to do it for this. So we're gonna put this problem on hold, and we're gonna focus on this problem. This problem is a brand new array. We're gonna start back from the beginning and say, how do we sort this? We need to break it down into its left half and right half. So the middle of this array is right there. So we're gonna split this down into a left half and a right half. The left half is going to be 17 and 3, and the right half is going to be 34 and 10. We're not even worrying about this yet. Now that we split it down into a left half and a right half, we're going to recursively call this procedure on the left half and put the right half on pause. So that says we're going to restart this problem thinking about this array. What is the midpoint of an array of size 2? The left half is going to be the first element, the right half is going to be the second element. So the middle point is right here. We're going to split this down into a left half and a right half. The left half is 17, the right half is 3. Now each of these are of size 1, so they are already sorted. So there's no further recursion going to happen at this level. So we're going to go back here, and the next thing we need to do at this level is to merge the sorted left half and right half. So what that says is to figure out what we're actually going to do with this, we're going to make a new array And we're gonna place a pointer here at index 0, here at index 0, and here at index 0. And what gets copied into this index 0 is gonna be whatever is the smallest of this value and this value. So what is smaller, 17 or 3? 3. So we're going to copy this into there, bumping up this pointer and this pointer. Since this pointer is now out of bounds, we're just going to continue to copy everything from this array all the way to the end. So we just continue to copy this until this is now full. So what we're going to do is we're going to replace this array with this array. So we've done all of this sub work now, so I'm just gonna kind of say we don't need it anymore. So all of this is now done, and this now points here. Now we go back to this level and we say, all right, we need to recursively sort the right half. So we're going to do that. The middle point is here. We're going to split this down into a left and a right. The left is 34, the right is 10. And now we have two arrays of size 1. So we return and we're ready to merge, which means that we're going to create a new array. And we're going to say whichever is smaller of these two things is going to go here. What is smaller, 34, 10? 10. We're going to write the 10 here. Bump up this and this. Now that this is out of bounds, we just copy everything remaining from this array. So we just copy the 34 over to there. Now we're done, so we can get rid of all of this. And this now points here. This is the right half. And now we have a sorted left half and right half. So we are basically ready to merge into this array. So to merge into this array, we need to make a new array of size 4 now. And we will note that the smallest element in all 4 of these positions is in one of index 0 here or index 0 here. And the largest element is at one of the rightmost positions. So now we ask which is smaller, 3 or 10? 3. We're going to write the 3 right here. We're going to bump up this pointer. We're going to bump up this pointer. Which is smaller, 17 or 10? 10. So you write that here. We bump up this pointer. We bump up this pointer. Which is smaller, 17 or 34? 17. So we're going to put this here. This is now out of bounds. We're going to copy everything that remains from this array, which is just the 34. And now we are done. So we erase all of this work. And the new left-hand side of the original problem now points at that sorted subarray. We did it. We sorted the original left half. Now we return to this level of recursion and say, well, we need to sort the right half. So we are going to do that. We originally put this sorting the right half on pause, but now it is time to break it down and start doing that sorting. So we're going to find the midpoint, break it down into a left half and a right half. The left half is 9 and 120. The right half is 8 and 1. Each of these break down further. We're going to put this on pause for a second, and we're going to break this down into 9 and 120. The arrays are of size 1, so we've hit our base case. They're already sorted. So we're going to go back and merge this into a new array. We put a pointer here, and a pointer here, which is smaller, 9 or 120. 9. We're now out of bounds, so we're going to copy over what remains, the 120. We put together exactly what we started with. There's no way for the computer to know that in advance, so we still have to go through this work, just in general. But now we delete all of this, and we replace that array with that array. Breaking this one down now, we have 8 and 1. We now make a new array, pointer here, pointer here, pointer here, which is smaller, 8 or 1. Now we're ready to get rid of all of this work and point the right half here. All right, we have a sorted left half and a right half at this level. So now we are ready to merge these into a new sorted array. So we're going to put pointers here and here and here. Which is smaller, 9 or 1? Which is smaller, 9 or 8? Now we're out of bounds here, so we can just copy the remainder of this array into that. So this is actually a great example because it shows that you can get the next smallest value from the same array. It doesn't just alternate arrays. We don't know that for sure. We can't assume it. So we'll just copy the remainder of the 9 and 120. I did not leave myself anywhere in that space for the 120, so I'm writing it vertically. Now that we have that, we can erase all of this work and point this there. And now we have the really fun job of merging the sorted left half and right half. So we are going to do that. We're going to make a solution array. Note that it's at the same level as this. I just don't want to draw it all the way over there. So we put pointers here, here, and here. We'll ask ourselves which is smaller, 3 or 1? 1. We bump up this pointer. We bump up this pointer. Which is smaller, 3 or 8? Bump up this pointer. Bump up this pointer. Which is smaller, 10 or 8? Bump up this pointer. We bump up this pointer, which is smaller, 10 or 9? Bump this up again. Bump this up again, which is smaller, 10 or 120? Bump up this pointer. Bump up this pointer, which is smaller, 17 or 120? I know, we asked the computer to do really thrilling things for us, don't we? Which is smaller, 34 or 120? 34. Now we're out of bounds in that array, so we can't just copy everything remaining in this one. And we did it. We sorted the whole array. We can now return this from whence it came as the sorted array. Did that seem like a lot of work? To sort something of size 8? Would we buy that this is more or less efficient than other sorts, like insertion sort, or selection sort, or bubble sort?
For being lives.
Maybe the recursion sometimes.
It's actually significantly faster. We actually ask a computer to do way more work with any of the other 3 sorts than we do for this one. Which is kind of crazy to think about how intuitive it is for us. But we have this lovely multi-threaded processor up here that's capable of looking at a large array and doing things like identifying the smallest element. Think of how easy that is for your brain. Just scan a large number of numbers and identify, hone in on where the smallest is. And then think of how many comparisons you ask the computer to do to figure that out. You do a lot less work than the computer does. And we have a lot of work to do just to identify where the smallest single element is. And with merge sort, this becomes one more level of recursion every time we double the size of the array. Has anyone tried to or heard of things like the guess to the number of folds of a piece of paper until the thickness of the piece of paper is the width of the observable universe? Taking a single sheet of paper, fold it in half, and you have 2 sheets of paper, fold it in half, you have 4 sheets of paper, fold it in half again, you have 8 sheets of paper. Now it's gonna start getting really hard to start folding things, but imagine you can continue doing this indefinitely. How many folds would you need for the height of that stack to be the width of the observable universe? Anyone have any guesses? The answer is somewhere in the 40s. That is the power of exponential scaling. And so whenever we can use the power of exponential scaling like this, we can use an array that is twice the size with one more level of this, an array of twice the size, one more level of this. We can solve an array with a number of elements, like the atoms, the width of the universe, with a recursive depth of not very high. Somewhere under 100. So it actually scales incredibly efficiently. So now that I've done the example on the board, I want to give people probably close to the rest of class and see if you can come up with a merge sort algorithm that works. So I recommend working in groups. If you'd rather work alone, that's fine. But if you'd rather work in groups, find some people to work with and see if you can implement this. Yeah, just assume it's an array that integers, don't make it any harder than it needs to be. I will keep this slide up because I think it has the most relevant information for you as you're going through this process. And no worries if you can't make it work, we're gonna do it together after this, but I think there are good outcomes associated with giving this your best effort ahead of being a solution.
What's the time complexity of this sort?
I was planning to talk about it later, but the answer is actually n log n. N log n. And we can talk about the reasoning behind that. So the merge process requires n steps or some number related to n steps. Because we need to fill that new larger array for each element that is in it. But how many times are we doing that process? Since we're splitting the array in half, we're doing it proportional to the log of the size. So n, we have log n merges that take n time. So that is down significantly from n squared. Log n is n log n is much closer to n than it is to n squared. We will find that the generic sorts that we consider to be advanced usable sorts are all n log n. But there are some sorts that work on very specific kinds of data in ways that are straight up linear. We can talk about a couple of those as time permits. Anyone have any questions before you get started with this process? You should take in the array, but you do not need to return anything because you are passing by reference. Even though you're making a new array, at the end, all you need to do is shallow copy. So I guess I can draw this out, maybe that will make more sense. If you have an original array, I'm going to draw this out as something that is unsorted. And eventually, you originally have a reference variable. I'm going to call this something like, I don't know, ARR. This is the array we care about. This is a reference variable, and this is the actual array structure. You have this pointed at that. And then you take this in as a parameter. Take in this unsorted list. What you can do is you can make a new object that is the sorted. And then all you do is ARR equals sorted, and this takes this reference variable, and instead of pointing it here, now points it here. And you don't need to return that, because ARR is all done and ready for you. It just looks like magic from the scope of this, where they said they passed in an array, they wanted that array to be sorted, and voila, it's sorted. Even though it's a completely different structure than was originally passed in, there's no way for them to know that because the reference variable stayed the same. If you have any questions or get stuck, let me know. I'd be happy to help.
Is using one again, the array sort and object, and then it's like, really
Shouldn't matter. I think you can use the primitives and be fine. This, we want it to be the integer because an array list can't sort primitive types.
we use loops.
You can use loops. You will need to use loops for things like filling the array as part of the merge process.
Where we have to use a loop to get our left and our right paths.
Nope. You should be able to, with a single expression, identify a midpoint.
Yeah.
And then you may want to do things like pass the starting and ending index of something into. There are lots of ways you can do this. You may need some additional parameters. You may be able to get by without additional parameters. Virtual requires.
Yeah. I got the cheapest one. I like 2 coffees for the rest. That's. Yeah, extra difference, that's for sure.
It tastes sweeter than.
It basically was just like the 49ers being. That was shit.
We needed that.
Absolutely.
Yeah, so I would say do something like, you can either make new arrays that are the left half and the right half, and then just call them. So that you're gonna, the recursive call is gonna be right next to each other, so as soon as you identify what the left half is, you're gonna pass that on, so either you want indices into the existing array and pass those down as additional parameters, or you want a new array that is pointing at the left half. Or a new array pointing at the right, half. It's called recursive deployment. 103.
103.
Full paper 100
It's plenty of copies. You have to make it more, just say 8. 8 is also impossible, regardless of the thickness of the paper, you cannot fold it 8 times, it just physically won't.
Do I have to fold it?
You want to bet, you want to bet a copy on that 8 one? I'm a betting man today, you know.
Okay, what, do I have to fold it down every time instead of going?
Yeah.
Okay. So I could just fold every corner.
Yeah, yeah, it has to be exactly a half. We can really do the best with students, is we can say, well, you can opt out of the 8, you just have to take the 8.
That's smart. That's some people would try. The regular session slides, we started on the right.
Yeah.
It's the way.
Yeah, but I think we have to choose. I need to choose one.
Probably still, if you. If you want to talk about this,
Yeah.
but to. Okay.
Yeah.
How would you?
I don't even know.
How are people doing with this?
Use like actually word them, you could like array. Since your original array is left in
Yeah, so you could use, if you want to make this, getting this to work might be a little bit challenging. You have a few walk by one errors, but you can use system.array copy. That takes a source array, a source position in the array, destination array, a destination position in the array, and a length, and it just copies length elements from the source array to the destination array.
Well, I was gonna still say, there's.
Yeah, you definitely need, but once you run out the end of one, then you can just copy, however many are left, you can copy them. But yeah, you need to use some kind of if statement to compare, and then kind of what I did on the board, just copy that element, bump up that index. And you do that while both indices are in bounds, and then you can do something else about that. Lots of ways.
Exactly, because it's the base case.
So I guess basically this is where it would be.
Fortunately, we are out of time. My challenge to people at some point between now and next Monday's class, tomorrow we're doing our exam review and Friday we're taking an exam, is do what you can to finish this off. And we will go over a solution for it on Monday.